Hello, everyone. Thanks for tuning in. So my name is Ben Moulton. I'm a PhD student here at Utah State University. I'm going to talk a little bit about some evaluation we did on the trim solutions of a bio-inspired aircraft. So the purpose of this project is to take a look at a novel aircraft design. And So the idea is we take an aircraft like an F-16 and we cut off the vertical tail. That's what's pictured here. So you can see that there's no vertical tail. And we take this aircraft and we cut off the vertical tail and then we let the horizontal tail rotate. And shown here we have the different control surfaces. So we have our ailerons, we have our stabilators, and then we have our engine, and we also have our tail rotation. That's this guy outlined in purple. Um, and so something we noticed was that when we would study this aircraft, we would get an interesting trim solution, and we wanted to dig a little bit deeper into it. So what do I mean when I say trim solution? A trim solution is a given trim state and trim control, and that's this equation shown here at the bottom that will result in the dynamics being equal to zero. That basically means if we stuck the aircraft in that state and let it fly for forever, assuming it had all the fuel in the world, it would just stay there. And so when we looked at solving for the trim solution of this aircraft, we noticed that we generally got this guy pictured here over on the left. So we'd get a tail rotation that was large and negative. So what that means is that the left tail was down. And we thought that was a little interesting because looking at videos of birds in flight, they generally flew, it seemed, in a steady coordinated turn. They would generally fly with the tail near zero. So that's this guy here in the middle. Or they would fly with the tail positive. That's this guy here on the right. So that's with the tail right wing down. Um, and so that made us wonder, well, what if we initialized our trim solver with some random initial guess? So we were using a Newton-Raphson solver that you could give it an initial guess, and that would kind of encourage the trim solver to go in different directions. And we noticed that if we gave it random initial guesses, we would get various different trim solutions. So we'd get this one with the tail negative, with tail near zero, or we'd get one with the tail positive. And so the purpose of this paper was to look at these different trim solutions. Do they have different properties? You know, because we're getting multiple trim solutions using our trim solver, that means our optimization is under constraint. And so what are the different properties of these different trim solutions that we could, guarantee one or the other? Is there a way we could pre-select it? That was in air quotes. Is there a way we could pre-select it with a different initial guess? Do certain initial guesses tend to result in other trim solutions and things like that? So I'm going to hop right in. So these are the trim control surface inputs for the BIRE aircraft and the baseline aircraft. So the baseline aircraft is that fighter with that still has that vertical tail. Um, and I want to explain these plots a little bit because the legend will stay throughout this presentation. Um, so on the x-axis is the bank angle. So I want to clarify that these, all of the solutions I'm going to talk about here are for steady coordinated turn and and for one CG location. So the CG is at the nominal location. Um, and these are at a flight condition of 15,000 feet, Mach 0.6. So on the x-axis is the bank angle. Um, I'll use my fancy dancy laser pointer. So I have this bank angle over here on these x-axis. So as we turn further and further into these bank angles, we're pulling higher and higher G's. Um, and on the y-axis are the different control surface inputs. So over here on the left, we have our aileron. Over here in the middle, we have stabilator deflection. And over here on the right, we have tail rotation, deflection, and rudder deflection. And I'll get to why that is right now. So we have two different aircraft plotted on here, and four different markers. And I'll get to why that is. So the baseline aircraft, so that's the aircraft with the vertical tail, those are plotted with diamonds. You can see them, they kind of tend to lie right on top of these tail near zero solutions. Um, And then the second are these little circles. So that's the BIRE aircraft, and those are trim solutions where the tail rotation is basically near zero. So that's that middle guy right there. I'll circle it right here. And then back to the legend. So there's two more different trim solutions that tend to show up for the BIRE aircraft. And that's those are plotted here with a plus sign and a minus sign. So the plus sign indicates a positive tail rotation, and a minus sign indicates a negative tail rotation. So that's back to these pictures over here. Over here on the left, we have a tail negative um, uh, orientation, and over here on the right, we have a tail positive orientation. Okay, so back to these plots a little bit. There's just a couple things I wanted to talk about. The first is that because the CG is nominal for the markers shown here, we get an interesting trend in the stabulator deflections. You can see it kind of curves up as we go to higher and higher bank angles. And we notice that if we move the CG forward, that trend actually flips. It starts to curve down. Now, once again, we're only going to talk about one CG location today. For more information on that, you can take a look at the paper. The other trends that we noticed on these plots were in terms of these alternate trim solutions, is what I'll call these tail large positive, so right wing down, or tail large negative, so left wing down for the tail. And you can see that there's a bifurcation in aileron, so that's over here on the left, and in tail rotation over here on the right. And you can see kind of a mirrored effect for the stabilators here in the middle. Now there's a whole heckload of research that's gone into bifurcation theory and when systems show up and have these multiple equilibria. For sake of time and for the purposes of the paper, that's outside of the scope of what we did, but definitely some interesting future work for this topic. So the next thing I wanted to look at, so just to explain these plots once again. So on the x-axis we have bank angle, so higher and higher g's as we move over to the right. And over here on the left, on the y-axis, it's angle of attack in degrees. So as we move at higher and higher bank angles, we're at a higher angle of attack, which makes sense. And then over here on the right is sideslip angle. And something to notice once again is we have this bifurcation in sideslip. So the tail near zero solutions tend to lie pretty close to the baseline aircraft, but these alternate solutions split off and form this kind of pitchfork image. For sake of time, I'm not going to talk about change in heading angle or the rotation rates of the aircraft in these steady coordinated turns. For more information, you can check out the paper, but those also have these bifurcations as well. Okay, so we've talked a little bit about the control surface inputs that the alternate trim solutions tend to have greater or use greater control energy, so they deflect the surfaces far more. Something else that we found was interesting. So you can take a look at these plots. Over here on the left, we have the throttle setting um, for these trim solutions, and over here on the right, we have drag coefficient. And you can see that generally the baseline aircraft uses a higher throttle setting and a higher drag coefficient. You know, there's a bank angle at which that's no longer true. You can see that the tail near zero solutions are higher over here. But more specifically, we wanted to take a look at what is the difference between these tail near zero solutions for the BIRE aircraft and these alternate solutions. So tail large and positive, tail large and negative. And that's plotted here. So this is once again the difference between these alternate solutions and the tail near zero solution. And you can see that generally these alternate solutions are lower in terms of throttle setting, so they require less propulsive power, excuse me, and they're also lower in terms of drag, so which makes sense, right? They're correlated, and so they incur less drag. Okay, and once again, these are the alternate solutions. Okay, so something else we wanted to take a look at was the stability of the system. Now, generally, when we talk about stability, it's difficult to do more than give it just a Boolean metric. You know, we're stable or we're not. Our eigenvalues are in the left half plane or they're not all in the left half plane. particularly for these nonlinear types of systems. But something we can do is we can look at the eigenvalues of the linearized system, and that gives us a little bit of information about the nonlinear system. You know, it doesn't guarantee everything for the nonlinear system, but it does say close to this trim location or this trim solution, these are the properties for our aircraft or system or whatever. And so you can see the equations up here um, in the top left. So over here on the right side of this slide, you can see on the x-axis is the eigenvalue. So these are all positive. We're in the right half plane. We're unstable, which makes sense because the baseline aircraft is statically unstable. If we cut off the vertical tail, we're not going to improve the stability. And so you can see the what are generally the short period unstable eigenvalues here. Now, you can see the baseline aircraft kind of stays the same. The tail near zero solution, BIRE aircraft kind of is a little close to the BIRE aircraft. Generally, the most positive eigenvalue is more unstable for the BIRE aircraft than for the baseline aircraft. Of course, we get to this point out here where the baseline aircraft is more. The most positive eigenvalue is greater than that for the BIRE aircraft. But something we found was interesting was that these alternate trim solutions, so tail positive, once again, tail positive, tail negative, these alternate trim solutions tend to have an even greater most positive eigenvalue of the system than for the tail near zero systems. Now, what does that mean? That means the linearized system for the BIRE aircraft will generally diverge more quickly for the alternate when this linearized system is done about an alternate trim solution than it would if it was done about this tail near zero trim solution. And we'll wrap things up at the end and explain a little bit what this all means. So there were a couple last metrics we looked at. The first was controllability. Now, once again, controllability, similar to stability, is a Boolean metric. It's you're controllable or you're not. It means you can go from the origin to some place in your domain, given infinite control energy, infinite time, for a simplified description. But and all of the trim solutions that we looked at were controllable. But so we wanted to look at maybe a better way to differentiate these different trim solutions. And so we settled on degree of controllability. And for a more mathematical description, you can take a look at the paper. But degree of controllability is basically a measure of efficiency in using a given control effector to dampen out some disturbance. And so these plots here on the x-axis, we have bank angle, so higher and higher g's as we go to the right. And then over here on the left, these are the degree of controllability of damping out a disturbance in yaw rate. Now over here on the left, this is using aileron. In the middle, it's using stabilator. And on the right, it's using tail rotation or rudder. Now, something to note is that we have flipped the y-axis over here. So generally we want a smaller degree of controllability that indicates a greater efficiency in using a given control effector for damping out a given disturbance in a state. Now we've flipped the y-axis. What does that mean? That means that we want to be higher up on these plots. So just taking a look at this plot over here, these tail near zero solutions are generally less efficient. In other words, using aileron to dampen out a disturbance in yaw rate, it is generally less efficient for the BIRE aircraft with the tail near zero than it is for the baseline aircraft, which makes sense, right? We've got a rudder on the baseline aircraft, and so it generally is able to do things a little bit better. Now, something we thought was interesting, and I'll circle these guys, is that these alternate solutions tended to have a lower degree of controllability, which means a higher amount of efficiency in damping out these disturbances, plotted here, for example, in yaw rate, than the tail near zero solutions. And you can see that over here we have these tail near zero solutions below it, and below it over here. And for more information, you can take a look at the paper. We looked at roll, pitch, and yaw for all these CG locations and flight conditions. Okay, so now that we've talked a little bit about the different properties of these trim solutions, I wanted to look at where do these alternate trim solutions even show up? So over here on the right, we have changes in CG location. So all of the plots we've looked at this point were involving these markers right here. So as a function of bank angle on the y-axis and a 0 CG shift. And you can see that as so once again, the circles are tail near 0. Each of these markers that you see here has a plus sign and a diagonal sign. That was done to help differentiate because the minus sign would lie on top of the plus sign. Um, and so we get this region where these alternate solutions show up. And it's a function of the center of gravity and of the bank angle. And so the idea here is that it gives us a little bit of an understanding of where we can expect these alternate trim solutions to show up. And we did notice that that tended to be mirrored for example, if we were to look at negative bank angles, we would kind of see this plot mirror across the x-axis down here. We'd get these alternate solutions where I'm showing my laser pointer. Okay, so the last thing we looked at was given random initial guesses in, alpha, beta control inputs, given random initial guesses, could we basically pre-select, once again in air quotes, where our trim solution ended up, given from our initial guess? And so we noticed that it was generally the easiest way to determine it was to use guesses in tail rotation. Those are shown here on the y-axis. Um, and then in stabilator deflection over here on the x-axis. Now, something to note is that each of these boxes in the plot, the more white the box is, that indicates that all or almost all of the trim solutions that started in that box resulted in the plotted trim solution. And the gray or darker gray boxes indicate that all or almost all trim solutions that started in that box did not result in the plotted trim solution. Um, and so you can see our three different trim solutions over here. Over here on the left, we have our tail negative. Over here in the middle, we have our tail near 0. And over here on the right, we have our tail positive trim solutions. And so generally what this means is if we initialize our Newton-Raphson trim solver with a large negative tail rotation, a large negative stabilator deflection, we would result in a negative tail rotation trim solution. Over here in the middle, if we start with a tail near 0 trim solution, or initial guess, and large positive stabilator deflection will result in the tail near 0 trim solution. And if we, over here on the right, if we start with a large positive tail rotation and a large negative stabilator deflection, will result in a positive tail rotation trim solution. Now, just to wrap things up, so we noticed that these alternate solutions, so where the tail is positive or tail is negative, or in other words, so tail positive is with the tail right wing down, tail negative is with the tail left wing down. These alternate trim solutions tended to result in the lowest propulsive input, the lowest drag. They also resulted in the most positive eigenvalues for the linearized system. In other words, they would diverge more quickly. And they also had the greater efficiency in terms of degree of controllability. On the flip side, these tail near 0 solutions tended to require less control energy. In other words, they wouldn't deflect as high, the control surfaces, and they also tended to have the least divergence of the linearized system. So what does all of this mean? It means, let's say we're going to build our little RC fixed wing drone or something like that. If we're going to set it in a loiter pattern, perhaps it would be best to stick it in a more efficient trim solution. So that's what these alternate trim solutions are. But perhaps we're going to make our aircraft more maneuverable, more agile. We would probably want to have the tail near 0 or building controllers or something like that. We're analyzing these trim solutions where the tail is near 0. Thank you for listening. This work was funded by the Air Force Office of Scientific Research through the Air Force Research Lab. Thank you.